Good afternoon, everybody. Welcome to a Wednesday afternoon, cold but sunny Wednesday afternoon of Chem 170 with your host, me, Dr. White. Now, what I was just doing was opening up something that I'm going to share with you that I just posted. Everybody see test number 4 information? Thumbs up, people. Do you see it? Thank you. All right, let's go through this. I just posted it. Well, yeah, 11:30. All right. On a week from today, the 4th of May. Wow, it's already May. Where's this year going? I will be giving test number 4, and it'll be online just like I've done the other tests. You'll be able to, you will be downloading a password protected PDF file for test number 4 from the assignment area D2L, and I'll have that available next Tuesday afternoon sometime. On Wednesday, when we end class, about 2:30 or maybe even a little earlier, I will send out via email the password for test number 4 PDF file. You'll have until Thursday morning, 11 a.m. to finish test number 4. Upload your test number 4 answers to assignment area D2L. Test number 4, historically, and I've taught this class long enough, I know how long my tests are. Surprise, surprise. Should take you about 40 minutes, but since I'm sitting in such a good, generous mood, if you need up to 2 hours, go ahead and take it. Now, test number 4, I say 4, will cover polymers, lipids, carbohydrates. Remember, lipids are fats and oils and steroids. And test number 4 has 9 pages, 20 problems. Some of the problems have multiple parts. Now, here's a point breakdown for test number 4. General knowledge, 54 points. Yes, 54 points. Nomenclature, 15. Reactions, 36. It adds up to 105. So there's 5 bonus points. As always, this test is not, as with all my tests, and the final 2 will not be an open notes test. I have secret stuff in there I can tell if you do. Please don't. And I will do a review of test number 4 material on this coming Monday Zoom meeting. On Monday, why do I have both of those? No, I'm going to have the Monday meeting on Thursday. Not. But anyways, we'll have our regular Zoom meeting next Wednesday. And when we're done with the lab and other material I'll cover, then I'll send out the email. Now, important note, please note that the extra credit project deadline is the 5th of May, the end of the day. If you are planning on doing the project, remember it's optional, but it's worth 10, yes, 5 and 5, 10 big points. You get everything right. I would highly recommend, well in advance of the deadline, send me via email your project. I'll look at it, and if there's anything wrong, I'll help you correct it. That way there should be no problem. Any of you who want to do this shouldn't be able to get 10 points. Now let's go back up here to the point breakdown. 54 points, general knowledge? Well, let's think about that. If I ask you, is my right or left hand, right hand, left hand, is my right hand chiral or not? Well, that's not nomenclature. That's definitely not reactions. So it must be general knowledge. If I ask you to draw the enantiomer of this molecule, well, that's not nomenclature. It's not reactions. Oh, it must be general knowledge, which is why those types of questions, there's so many points on general knowledge. And that's why it's up to 54 points. So that's the breakdown for test number 4, and I'll be giving it a week from today. So make sure you start doing the problem set. Speaking about problem set, on Monday, along with my world famous review for next test, test number 4, I will also be going through the carbohydrate problem set. All right, any questions about test number 4 coming up? Now, one thing, public service announcement for me, Dr. White. For some reason, students think, oh, it's not that hard. I don't have to learn any new reactions, except for a variation of one. And so I don't have to study hard, and they don't. And you know what happens? The test scores go down. Study for test number 4, just like if you needed every point, which is always a good way to study for a test, but study hard. Don't think, oh, it's not that hard. I don't have to study that hard. Practice, please. All right, any questions on test number 4? Going once, going twice. All right. Now, on Monday, I was going through and reviewing some important things you should know from the chapter on carbohydrates. And what I was talking about, I had ended up, remember the reaction of methanol. And that reaction was, in general, if you take an alcohol and react it with acid with a hemiacetal when R prime is H, or hemiketal when R prime is carbons, what happens? You replace this hydroxyl group with the OR triple prime from the alcohol you're reacting that molecule with. Everything else that was attached to this carbon with 2 oxygens, oops, oh no, I got it there, but I forgot an oxygen, and it's attached to that carbon. And so where this plays a role is in starch formations. But to make your life easier, don't tell anybody I'm doing that. Oops. Wow, that was a lot to draw. Question is, give the organic product or products 3 points each. Your turn. Why don't you try this? And hint, and when you're done, give me a thumbs up emoji, or if you have your webcam on, you can put it, give me a thumbs up. Thank you, Vivian. Thank you, Christian. Those of you who haven't turned your webcam on all semester, I'm thinking maybe by the end of the semester, I'm going to have a one-on-one so I get to meet you. All right, I think everybody's done. Let's take a look at this. If we look at this molecule, what's different? Well, there's a lot. There's an alcohol here. Oh, wait. Oxygen on this carbon, hydroxyl group of hydrogen carbons. This is the cyclic form of glucose, and it's this molecule, a hemiacetal. And this is an alcohol, acid catalyst. This is the reaction. The only thing that will change is this. So whatever is not changed or involved in the reaction, I can rewrite. And don't forget this bond right here is still there. And the only change is this becomes this, which is this group will now become this. What's our R group? Well, in case you forgot, I like T-butyl groups, so that's what I gave you. And that's how you do it. Now, a couple things. First of all, for this reaction, I will never give you a synthesis problem, give the starting material on this one. All right, now, why is this important? Good question. Let me show you. Two days later, I'll be finished. If you look like you're seeing double on the screen, you are. Now let's take a look at this. Both are glucose in their cyclic form. And this reaction up here, notice an alcohol plus a hemiacetal gives me this acetal or ketal. Well, in this case, here is my alcohol. Here is the hydroxyl group I'll replace. And it does. And what you see is this. Now, I have a glucose bonded to another glucose. And this is a acetal linkage or bond or linkage, as I like to say. Is that a word I just made up? I don't know. But anyways, what does this mean? Well, how was it formed? Well, this reaction up here. If you notice, if I had another glucose molecule, it could react here. And as I showed you, you could put together many of these. So if I were to take lots of glucose and react it together with itself with an acid catalyst, in case I think I mentioned this once before, good acid catalysts in your body are called enzymes. Many of the enzymes are just very, very elegant, fancy acid catalysts. And what do you get? Starch. Now, for sucrose, what is sucrose? It's fructose and glucose bonded together. And if I take acid, what happens? Same type of reaction I just showed you, but here you get sucrose, which you know as either sugar or table sugar. I guess because you find it on your table. Is there some product called floor sugar or seat sugar? Nah. All right. Now, in test number 2, you learned the following reaction. If you take an acetal or ketal, react it with water and acid, you get back the aldehyde or ketone you started with. Keep your eye on the carbon with 2 oxygens, becomes this carbon, plus your alcohol. And if you wanted to balance it, you could put the 2 there. All right, now, what does this imply? Well, guess what? If you eat a starch, and in your stomach you have acid and water, which you do, what do you get? Well, if we go back here, you're going to break this linkage. And what will you end up with? Glucose. And this is how your body creates sugar. It transports in your blood to your various parts of your body that need carbohydrates, glucose, and does, which I have no idea what it does because I'm an organic chemist, and that's biology or biochemistry, which I haven't really studied. All right, now one more thing. I'm gonna let you try this one. And why don't you try that one? What would you get if you react sucrose, like in your stomach, with acid and water? Your turn. And when you're done, give me a thumbs up. And the thumbs up have spoken. Well, what's sucrose? It's fructose and glucose held together by an acetal ketal linkage. So what do you get back? Glucose plus fructose. So these are 2 important reactions that go on in your stomach. That's how you break down starch. That's how you break down a disaccharide. 2 monosaccharides bond together, we call sugar, table sugar. Actually, mono and disaccharides are glucose and fructose are also sugar, but most people don't relate to that. All right, now, leaving my class, there's a couple important things you should know. Hint, the first one is, how do you describe with the words in a general reaction what happens when you eat something with a fat or oil in it? And how do you describe that? What's the functional group in a fat or oil? And the answer is an ester. So when you eat a fat or oil, I should say containing food, how do you describe that reaction in your stomach with words? Well, in your stomach, you have acid and water, so that's an acid hydrolysis of an ester. And what's the general reaction that you learned for test number 3? And the answer is ester acid and water. You get back the carboxylic acid plus the alcohol you would have used to make that. In this case, in your body, I'm not going to ask that, but think about it. You're making glycerin and fatty acids. I wonder what the body does with glycerin. I'll have to look that up next year or two. All right, this is what happens when you eat a fat or oil. Again, you should know how to describe with words, and that's acid hydrolysis of an ester, because the functional group, the key one in fats and oils, is an ester. And the general reaction, which you learned for test number 3, is ester, acid, water. You get back the carboxylic acid plus the alcohol you would have used to make that ester. And now, as you just learned, what happens when you eat a carbohydrate? I really should put down starch, but this is better. And how do you describe that with words? You should know. Well, what's in your stomach? Acid. And what else? Water. So this is acid hydrolysis of, and in starch, what's the key functional group that you're breaking? An acetal. And how do you describe this with a general reaction? Well, you learned for test number 2, acetal or ketal reacted with acid and water. By the way, one of the miracles of life in my mind is in my body and your body and your stomach, you have cells that synthesize hydrochloric acid. I find that mind-blowing. Did you see the top of my head blow off? No, that was awful. I hope I never say that again. Sorry for inflicting emotional pain on you. But anyways, we have an acetal or ketal, acid and water. What do you get back? You get back the ketone or aldehyde you would have used to make that acetal or ketal, plus the alcohol you would have used to make that. And there might be 2 here, but in a carbohydrate, these are connected together, which you don't have to put the dots I just did in there, but I just thought I'd mention that. And when they're connected together, we call that glucose. So you should know how to describe with words and a general reaction what happens when you eat a carbohydrate. What's the key functional group holding glucose together in a carbohydrate or a starch? An acetal. And therefore, in your stomach, acid, water, acid hydrolysis of an acetal. And here's the general reaction. All right. But you didn't think you were doing all those chemical reactions when you had lunch today or breakfast this morning, but you are. Do you know you're a walking chemical plant? Now, another thing that I would like you to know, and leaving my class, and that is how does soap work? First, you should know what's the structure of soap. And all soaps have a nonpolar tail and a polar head. And let me scroll down a second. When you're washing, say, your hands, you use water, and water is polar. And what are you trying to get off your hands or wherever you're cleaning? Either dirt or grease. And these are nonpolar. And the key to the puzzle, how does soap work, is the following. Like dissolves like. I wonder if I could have written that in a larger font. All right, so what does that mean? Let's look at a piece of dirt. And when you have a piece of dirt, which this is highly magnified, didn't know I could do that, but I can. Soap molecules look at dirt, which is nonpolar, and the nonpolar tail says, oh, I know like dissolve like. You're nonpolar, my tail is nonpolar, so we'll line up like this. Now I'm just going to do a few soap molecules, but this surrounds the dirt totally, all 360 degrees in a sphere. And we call this, which you should know, a micelle. And now the dirt particle, the outer part, is surrounded by polar heads. So water looks, didn't know water had eyes, did you? Well, that was bad. Looks at the micelle. And says, oh, micelle, you're polar, I'm polar, let's go down the drain together. And that's how it gets it off your hands. And you should know this. Let's go through it again. How does soap work? Soap, nonpolar tail, polar head. Remember, water is polar, dirt and grease are nonpolar. And the key to this puzzle is like dissolves like. And what that means is things that are polar are soluble in polar things, things that are non-polar are soluble in non-polar things. And if you mix two together, they're not soluble. Well, water and dirt, that's why you can't use just plain water to get dirt off things, because one's polar, one's non-polar. But when you use a surfactant, something that interacts at the surface of two different things, like dirt in your hand and water, actually more than two different things, you have dirt interacts with the nonpolar tail of soap. So the polar head is on the outside, the tail is by the dirt, and this forms a micelle, and the micelle has the polar heads all around the dirt, and water looks at the micelle and says, I don't know if it says, but it says, I'm polar, You're polar micelle. Let's go down the drain together. And they do. All right, one other thing I'd like to review. Is what's the product of this equilibrium? I'm going to let you try it first, and I'll do it. And I think everybody's done, so I better get to work. Well, if we look at this molecule, I have an aldehyde, and at C5, carbon number 5, I have an alcohol. And if you have an aldehyde, or ketone, now when it's not intramolecular in the same molecule, meaning in separate molecules, you need a catalyst. But when they're in the same molecule, you don't. And this attacks that. Remember, organic chemists are violent. What's attached to what was the carbonyl carbon is still attached, and now you have this OR and also hydroxyl group. Well, here's our carbonyl carbon, here's our alcohol. This attacks like that, this attacks there. And what's not involved in the reaction doesn't change. And this oxygen, which is this oxygen, becomes this oxygen bond to that carbon. So I will. That's not an arrow, that's the actual bond. And then that will also have a hydroxyl group. And you should know how to do this. Hint. I'll give you a chance to check your answer. All right, let's do for fructose. Big hint, which I won't do on this test. And again, your turn. And remember, both of these reactions, I could ask for either the product or the starting material. And when you're done, give me a thumbs. I'll use the poll. Hold on. There you go. Everybody's done, so I better get to work. If we look at this fruit, this is fructose. We have a ketone right here. Again, this is fructose. And here, same reaction. If it was in separate molecules, you need an acid catalyst, because it's intramolecular. This attacks that, and this hydroxyl group attacks that carbonyl, same way. And what's not involved in the reaction I can just redraw. But what does change is this oxygen with the R is the hydroxyl group, this oxygen, this alcohol, and it bonds to the carbonyl carbon, and that has a hydroxyl group. And if this didn't happen, we wouldn't have table sugar. That's sad. And that's how you do it. Now, if I look at the clock, I've got a little time before we take a break. I was thinking, what can I do to teach you something about the real world? Ooh, that's scary. And I was thinking, let me teach you about problem solving in the real world. And in case my real world, in a chemical plant. Now, when I was working for Axo-Chemie, this was the plant and the research center has been long torn down, but it was in McCook, a couple of miles from Brookfield Zoo, right off First Avenue, and 47 on 47 in McCook, which is right by Brookfield Zoo. Part of my job was when there was a problem in this plant, I'd get a call and say, you and your group solve it now. Well, one day I got a call in the morning, and this location had a research center, and right down the block, like about a half block walk from our research center, was a chemical plant. The other chemical plant Axo had in Illinois and still does is in not McCook. I got a mental break. Morris, Illinois. See what happens when you get gray hair? But anyways, and more, I haven't thought about that name in many years. Anyways, so I get this call from the plant manager and says, we got a problem. I said, what? Well, this reaction to make this product, and it's called an amine oxide, is a functional group I haven't taught you about. We just ran it, and out of the reactor, foam shot a couple hundred yards into the sky. that shouldn't happen. I said, no, you've been running that reaction for decades. And he said, well, help, we don't know what's going on. So the first thing I did in problem solving is make sure what people are telling you the problem is. So I sent one of my chemists over to the plant. It was right next door. I said, get a sample of each chemical they used for that reaction and bring it back to the lab. And they did. And we went in the lab and did the same reaction. Guess what? It foamed up, and it shouldn't. Well, one of my best mentors I ever had in my life, and that was Sid Shapiro, who was at Axel. Sid was, when I started, I was starting the chemical industry. I just gotten my PhD, finished being a postdoctoral fellow. This was my first job in the chemical industry. Actually, I'd been there for a while because I was now section head, but Sid taught me a lot. One of the things he always beat into my head was common sense is not common. And you always say, common sense is not common, Sonny. And Sid was at that point about 50 years older than I was. And so he'd call me Sonny. And I'd always joke back, you're not my father. And he'd laugh and we'd laugh. But he kept on reminding me. So common sense is not common. But what would common sense tell you? Something we've done for years now isn't working. Something's different, something changed. So what you don't know, but I'll teach you, is this, the main starting material for this reaction was made in our other plant in Morris. So immediately I called up the plant manager, who I knew quite well at Morris, and said, this amine that's used to make the amine oxide that you just sent over to McCook, are you doing anything different the way you're making it? And he shouldn't have, because we had strict rules that the plant manager shouldn't change reactions. Unfortunately, they didn't always follow those rules. Well, he said, yeah, we tried something different. It worked. What? Well, in the reaction, what you would do is make this product, and you make in the product water during the reaction. And you take it to Carl's, a conical tank, and you put it in there. The water would separate from the product, and you would drain it off and then ship the product to the other plant. He said, that takes a lot of time. And I was thinking, we can pull a vacuum on this reactor and pull the water off. You should have learned in general chemistry, when you lower the pressure where you're doing it, boiling something, you can boil it at a much lower temperature. And they are doing what's called a vacuum distillation. I taught you about distillations. Well, what he didn't think about was one of the reactants that came out with the water when you dropped it in the conical tank did not get sucked out. And that was acetic acid catalyst. And in the next reaction, they used peroxide, hydrogen peroxide, with the tertiary amine. And that made what's called an amine oxide. And what happened was the peroxide, and this is a reaction I didn't teach you, but I know, reacted with the acetic acid to make a per-acid. And when that was heated up in that reaction in McCook, it decomposed violently to make oxygen, which is a gas, plus acetic acid again. And that's what made the foam, because all that oxygen being boom. And so I first of all, I didn't use profanity, but I yelled quite profusely at the plant manager at Morris. We were friends, but I still let him know, don't do this again. If you're going to make changes, never experiment at a plant level. And Sid taught me that too. Call me up. I'll have a chemist test it and see if there are any problems. We would have caught that. And he apologized. And I said, all right, you need to make some more of this and ship it to McCook. And when they did, before they ran it again, I had a chemist get some of the chemical and try it in our lab, and it was fine. So what I wanted to teach you today is problem solving 101. And when there's a difference, something goes wrong, and it was all right before, that means something has changed. And to solve the problem, you need to find out what changed. Now, years later at another company, they're trying to close down this one plant outside of Milwaukee and move those products to a plant in Ohio. I think was it Columbus or no, outside actually in Toledo. And it was an area I was not responsible for. And because this product was for our best customer, General Motors, they said, until you can make it successfully in Toledo, don't close down the Milwaukee plant. Well, that was about $100,000 a month, keeping that plant open until they could successfully make it in Toledo. And after 6 months, that's over $500,000 being wasted. The research director called me in at this new company I was at. I'd already made a name for myself solving problems. He said, I need your help. I said, well, how can I help? He said, solve this problem. I said, that's not my area. I don't know anything about it. He says, I know, but solve it anyways. And I did. What they're doing in Toledo, the plant manager, in Milwaukee, the plant manager in Toledo, so I don't want to do it that way, and made some changes. And when you did it the same way, guess what happened? It worked. And one of the things I did was I went to Milwaukee and watched, and I actually videotaped them making that product. And then I went down to Toledo and watched and videotaped them making that product there. And I could immediately see they're doing something different. All right, with that, let's take a 5-minute break and we'll come back and do our lab. I'll see you in 5 at 1:55. Ooh, Dr. White knows his math. forgot to turn my mic on. Let me do that again. Time to get work again. All right, it's lab time. Dr. White's sad. Why am I sad? Because this is a lab that's so much fun to watch students do face to face. But good news, some of it, if you want to, you can do in your house or outside in your backyard or somebody else's backyard. And what's this lab? Well, as I mentioned, I'm pretty sure I mentioned, when I inherited this course many years ago, the labs that were with the course were awful. I mean, awful, awful. I mean, awful, awful, awful. They were terrible. And I challenged myself. And the challenge was, because if you look in the catalog for this class, it's a 2-hour, actually an hour and 50-minute lab. At other schools, and I teach at COD, the lab is 2 hours and 50 minutes, which means I can't use any lab books that are published, because those are all at least 2.5-hour labs. And this lab is for only an hour and 50 minutes. So I challenged myself, can I write labs for the whole semester that are educational, fun, and don't cost a lot of money, or any, very little. And I did. And I needed one more lab after I'd written the other ones, which you've seen so far this semester. And I was challenged. I said, I've got to really challenge myself. How can I do the following? What am I an expert in? And the answer is surfactants. So let's have a lab in surfactants. And at the same time, what do I know? Well, for many decades, I worked as a research and development manager in the chemical industry. So how can I make something with surfactants, an area I know quite well, and make it fun? That's always an important thing. Students don't like unfun. Is that a word? Unfun labs, and give the students a real world experience. And I came up with today's lab, which was a hit, always is. One of the things, dangerous things about this lab is I bring a camera to the lab. I tell students, any pictures I take is just for me personally, because if I ever put it on social media, you can put it, sue me and sue the school. And trust me, I don't need to be sued ever. And so, but I have a bad habit, put a camera in my hands and I can be beyond obnoxious. I mean, bad. And I had the camera I have that I would take to these labs. I have a flash drive that holds 500 pictures. And in a 2-hour 50 lab with 24 students, I usually can take about 300 or more pictures. Students start giving me these dirty looks. Oh, aren't you done yet? No, I'm having fun with my camera. Like I said, I can be obnoxious. So what is this lab? This lab is called Developing Competitive Products, or what's the title I have? Developing Competitive Products. Now, what's this lab about? Well, when I worked in the chemical industry, a couple of companies where I was a research development manager, one of my, probably the important part of my job was to work with marketing, sales, vice president of marketing and sales, the marketing sales group, to develop new products that the company could sell and make money. And that's why I was hired. That was the, I also did problem solving, but the key job was to help make money with new products. And one of the areas that I got asked to do would be the VP of marketing and sales, or the marketing manager or sales manager, head of sales, would come to me, or I'd be in a meeting and they'd say, our competitor makes this and we don't have anything like it. We need something so we can sell something like it and make money. And that's how you do competitive products. So today, you have just been officially made part of my research group. And our job today is to develop a competitive product. Well, what is this? Well, I was in a meeting with the vice president of marketing, sales, and others, and the competitive product, and let's see if I can find it on the internet, which I'm sure I can. Is to come up with a product like Miracle Super Bubbles. You see that? Or Super Miracle Bubbles? Everybody see that? And in the lab, we actually have this that I give a bottle to each group of each research group, each lab group to use, plus other things. Now, let's think about this. What's a bubble? Good question. Ooh, let me do something I can do on the internet. Now, if we were in a classroom or in the lab, I'd take it out, but since I'm in my office, I'm not going to blow bubbles. Oh, let's have some fun.
A family vacation in a Verbo means leaving all the...
No, I'm not going to pay money to get rid of the ads. Oh, come on. Let's try this again. And that's why I'm sad, because you'd be doing that, not the screaming part, in the lab. Now, the question is, when you go like this to the wand and a bubble comes out, what's a bubble? Well, let's take a look at that. Bet you never thought that was organic chemistry, but it is. Now, let's look at a super magnified bubble. And this is a bubble. What's outside the bubble? Air. What's inside the bubble? Air. And then you have this film right here that's made up of water plus surfactants. Now, what's the surfactant? Essentially, it's like a soap, or it can be a soap. You have a non-polar tail and a polar head. Now, air is non-polar, oxygen, nitrogen. Water, well, you know that's polar. And what helps make a bubble? Light dissolves light. Now, this is a different micelle than in dirt. Here, you have the non-polar tail wanting to be near the air. And the same thing here. And the polar head wants to be in the water. So all around this bubble, you have this form. And guess what these are? Another form of a micelle. And that's how a bubble works, is made. And what you need is water and surfactants. Now, one of the things I talked about the other day were patents, and that's a way of protecting what's called intellectual property. And you have three types, and I think I might have misnamed them. One's composition of matter, one's application, and the other is a process patent. And if you go to the United States Patent Office website, there are a lot of patents on making liquids that are used by children to make bubbles. And I mentioned it briefly, but I'll do it again. It costs a lot of money to file and create a patent. And therefore, if you're going to do that, you think what you're patenting is going to make you a lot of money. Well, let's look at this lab. Now, in this lab, you're going to be developing and testing different formulations of bubble making solutions. And the goal is, well, I figured out the ECC was never going to let me spend a couple of $10,000, $20,000 for equipment to measure bubbles for one lab. No way. But what could I have the students measure to show how good a bubble is and use that as a test? And the answer was blow a bubble and see how long it lasts until it pops. And so the commercial product, you would test and see how long the bubble lasts. And then you would make a bubble that lasts as long or longer. And what surfactants are we going to use? Well, I decided on three of them: dishwashing soap, liquid hand soap, and detergent, laundry detergent. Now, if you go and look at the patents, you can find people claiming that if you add polyhydroxy compounds, it can hydrogen bond and make better bubbles. And what are polyhydroxy compounds? Well, glycerin is one you can get your hands on, and corn syrup. Also, later on, I changed the corn syrup, I didn't do it on here, to starch you make in water. And so the question is, how do you test all these in a formulation? Now, there's something called design of experiment, which is called in the chemical industry DOE, design of experiment. And this is a way of coming up with a series of experiments that test a lot of variables quickly, because time is money. Now, one of the important lessons that I learned very early on in chemical research that a lot of chemists to this day forget: when you do experiments, you should only change one variable at a time. When you do experiments, you should only change one variable at a time. Well, if you're good at DOE, I am, you can set up a grid of experiments which you change one variable at a time, but you do it in a very quick and efficient way. And that's what I've done for you. And if we were face to face in this lab. Now, before we go any further, you should know, hint, dishwashing soap, Dawn, has this structure. And you have in our groups 12 carbons, CH3, CH2, CH2. then OCH2, CH2, which is anywhere from 3 to 5 moles of ethylene oxide react with an alcohol, and that ether alcohol, you react to make a sulfate head. So essentially what you have here, nonpolar tail, and right here, polar head. A surfactant. Now, if we go to liquid hand soap, which a lot of you have in your house, and we have in the lab, it's similar to Dawn, but different. This is called laureth sulfate. This is sodium lauryl sulfate, similar but different. And here you have your nonpolar tail, and this part is your polar head. Now, finally, if we go to our laundry detergent, and we use all, I've been using it for decades. That's what I had them buy. This is slightly different, but it's still similar. And that is, you have what's known as a linear alkyl sulfonate, or sulfate. Oops, made a mistake. Don't look. And here again, this part is the nonpolar tail. I'd highly write these down or come back to the videotape for this. And this is the polar head. So how do we do this? Well, let's take a look at the lab. In part A, you'll be testing the efficacy of the Dawn dishwashing soap. By the way, I think Dawn's the best. I've been using it for many years, happily. And to make bubble blowing solution. And you'll also test what happens if you add glycerin to your formulation and corn syrup. And you'll be doing these in beakers so you can put the wand in and blow the bubbles. Now here, we're going to do a series of 5 different solutions. A1 has 2 milliliters of Dawn and 18 milliliters of water. A2 has double the amount of Dawn because we add 2 and we've reduced the water amount, so it's double. And then A3 will take what was left of A1 and add 5 drops of glycerin. A4, you take what's left of A2 and you add 10 drops of glycerin. And you test these, and I'll talk about that in a second. And A5, you'll make another A2 and add 10 drops of the cornstarch solution. It's a solution in water. And you'll test this. And how do you test it? You blow bubbles and see how long they last. And then you take an average of your 5 best bubbles. Now, at this point, I tell students, if you listen carefully, if you try 10 times and you can't get even 1 bubble, put down 0 for the time. If you try 10 times and you can't get 1 bubble, put down 0. I also tell students now about proper etiquette in the lab with bubbles. It's not polite to burst your neighbor's bubbles. And it's also not polite to blow bubbles at your neighbors, or especially at me, Dr. White. But anyways, it's a fun lab. And here, if you were in the lab, first of all, you're going to test the commercial product. And that's your benchmark. And benchmark is you should get at least as good if you're going to try and get a good product to sell. And here you only do it once. but you write it in your lab notebook if we were doing it in real life. Each time you test it, you don't have to do it over again. I told the students that. And for this one, you measure in seconds and the average seconds lifetime. Here are the different formulations. Now that's using the Dawn. Now in part B, we're going to test the liquid hand soap. And the liquid hand soap, and here's where DOE, design of experiment, pops in. And I know how to do this. You'll have B1, which is 2 grams. The reason we don't use milliliters because this is much thicker and it'll take forever and a year to get it out of a graduated cylinder. So it's just the same as weighing it. And 18 milliliters of water. Notice that's similar to A1, except a different surfactant. Now the hand soap. And B2, you're doing similar to A2, but with a different surfactant, twice as much of the liquid hand soap. And that's where we added more soap, lowered the water, so it is twice as much. Now in B3, we have all of B1 after you've tested it and add the glycerin, similar to A. And in B4, before what? Well, I can't resist saying that, but in B4, we add B2 and 10 drops of the glycerin. And finally, B5, you take the B2, make it again, and add 10 drops of the cornstarch. And again, you blow bubbles and you measure the average time. And here's data. And since I've seen this so many times, it's really real world stuff. Now, in part C, we'll be doing the laundry detergent. And there, you're going to be doing the same type of formulations, but now we've changed to a different surfactant. But C2 is 2 milliliters of the laundry detergent, 18 milliliters of water. C2, you've doubled the amount of surfactant, the laundry detergent. Then in C3, we take the C1, add 5 drops of glycerin. C4, you take C2 and add 10 drops of glycerin. Finally, C5, you take C2 and add 10 drops of the cornstarch slurry or solution. And here are the measure. Whoa! Now, I'll do this now and I'll come back to this in a little while. Now, one of the things I don't have here, and you don't have to do part D, but a number of years ago, a student came up to me and said, Dr. White, can we try our own formulations in the lab? I said, that's a great idea. You got to use only the chemicals that we have out, the glycerin, the cornstarch, and the 3 different surfactants and water, and do your own formulation. And they loved it, and they tested it. Now, here's the fun part, real world. When I was a manager and I wasn't sure of something, somebody said, this is how it is. And before any report that got issued, I'd have to sign off on, literally. And before I did that and stuck my neck out, I would say, show me it works. And to make it real world, if we're in a lab, I'd say each person has to take their best formulation and both people in the group can use the same one. And you only have to blow 2 bubbles, except the big boss is watching me. And it's so funny to see people under stress. Well, not if you're a person under stress, but they know it's just fun. And once I see that, I actually sign off on the lab with my initials, which is why I have that already there typed in. Now, there are a couple things I need to talk about. One is that in real life, adding things to solutions make a difference in their performance, which I've showed you. Now, 2 things I'll teach you about. When I was at one company, part of my job was in charge of waste treatment for the plant that was on site. we had these huge raised treatment ponds, and one of them started foaming. And it was like 200 yards from 47th Street in Chicago. And if that foam hit the street and closed down that street, we would have been fined heavily. So the president of the company and my boss said, you better solve this quick. We only got a couple of days before we were trying to knock down the foam before it's going to hit the street. Well, I found a molecule. Now, what we're doing, what you're doing is looking at surfactants that make foam. What's foam? Just a lot of bubbles held together. But what I needed, they're surfactants that stop foam, and they're called defoamers. And luckily, I had some in the lab, and we experimented with this stuff that we got from the waste pond. And the one surfactant that did the best job, the only place I could buy it, and I needed 4 drums. Drums are 500 pounds, 450, 500 pounds, depending on density of the material in there, was in California. And I had them airship overnight 4 drums of chemicals. That cost a lot, was a lot less than millions in fines. To our plant, we put it in, and luckily it did the job. So there's foamers and defoamers. Now, let me tell you another story about defoamers. When I worked for this one company, Borden Chemical, when I got there, I found out the R&D managers, there are about 8 of us, and Friday afternoon after work, we go to this dive bar and sit around, have a few beers before we went home, and complain about our workers, complain about how dumb upper management was, and just get, vent. And it was nice, except for one thing. And that was the owner of this little dive bar had developed this interesting skill. What was that? Well, in a pitcher of beer, he could put a head of foam, at least a third of the pitcher. So you're getting less beer. And if you complained, he looked at you and said, go somewhere else if you don't like my place. Well, I wish I could say I did this, but I didn't. There was another R&D manager who knew surfactants as good as I do. And he was getting really mad. He didn't tell anybody, and he did something. Now, before I tell you what he did, any company that sells chemicals has what's known as a sample room. And if you have a customer or a potential customer who might use your product, you'll send them a sample free so they can test it, because you might get new business. And you can get all sorts of chemicals, if you have the right credentials, sent free of charge. If it's not that much, if it is that much, they'll ask the marketing manager for your company or your area, will you approve this? And if you're a big company and you're established, they still always say yes. Well, when it comes to samples, there's 2 types of chemicals. One is industrial chemicals, and the other is food grade chemicals. Now, both are very pure, but industrial chemicals are never meant to be consumed. Food grade chemicals, besides being chemically pure, they're, and I'm probably using the wrong term, biologically pure or safe to consume. So what this chemist did was he got a sample of food grade defoamer, where I'd gotten those barrels at that was industrial chemical. He got a couple ounces of a food grade. Then he got this little squeeze bottle with a thing on top that you can put drops in. And if you've ever been in a bar and you get pitchers, what does the bar do when it's empty? They'll take it, they'll rinse it in a soap sink, then they'll have 1 or 2 water sinks to rinse it out, and they'll hang it up to dry. Well, that day, the first pitcher, we were almost done. This guy said, shh, don't tell anybody. He took out his little bottle and put a lot of drops of that defoamer in the pitcher and shook it around. There wasn't that much, coated the inside and said, hey, we need a new pitcher. So we got one. They took that sinks, and what it did was contaminate all 3 sinks with defoamer. We stayed later that night. And after a little while, the pitchers were contaminated with the defoamer, and the owner couldn't put a head on the beer. He was getting mad too. And we started laughing. We had a few pictures by then. And he looked at us and saw we were laughing at him and everything, and said, "You guys are scientists. What did you do?" "Well, we didn't do anything." He said, "Get out of my place and never come back." We said, "Okay." We found another place that gave us a full pitcher of beer. So remember, there are foamers and defoamers. Now, I tell that story, and then students will come to me, say, "Dr. White, what's wrong with formulation C? We can't blow bubbles." What's the one place you never want foam or bubbles? A washing machine. And that's why they have in commercial laundry detergent defoamers. Now, when I tell that story to students after they ask me individually, I tell them, I've had a couple students tell me, or they say a friend, yeah, right, wink, wink, hint, hint, say no more, ran out of laundry detergent and used Dawn. And Dawn has a foamer. It makes foam. And guess what? When they put it in their washing machine, their whole utility room was covered in foam on the floor. It just bubbled right out of the washing machine. So don't do that. Now, one other last thing before I let you go. You've been conditioned by Madison Avenue commercials that when you wash your hands with soap or your dishes, oh, look, that's foam. That's good. Guess what? That foam has no bearing on forming micelles to clean your dishes or your hands. You've been conditioned. There are actually chemicals I can put in to make foam. They're not that good at surfactants in terms of cleaning, but they make foam. So I hate to tell you this, you've been conditioned. And with that, I'm going to say I'm done. Don't forget, Monday, I will be doing my world famous review for next test number 4. And I will also go through the carbohydrates problem set, and I'll start the last chapter. And that won't be on test 4, but I'll have a few questions on the final. It's coming up already. Oh, where did the semester go? Time flies when you're having fun with organic chemistry and Dr. White. With that, unless you're coming to my office hour tonight, which you're always welcome, I'm going to say, gang gesund, goodbye. I'll see you on Monday or tonight. Bye. Gang gesund.